Mr. Heffron here, and here's a video on reference frames, or frames of reference. A reference frame, or a frame of reference. In physics, this is a set of coordinates that can be used to determine the positions and velocities of objects in that frame. Basically, an observer uses the reference frame to describe the motion of other objects. So, for example, here's a car traveling south. And this person would say, hey, the car is moving to my right, coming from my left. And this person would say, hey, it's moving left, and it came from my right. So in this case, it might be nice to say, it came from the north, and it went south, less of an argument. So there are two categories for reference frames. There's your inertial, where there's a constant velocity, and non-inertial, where the observer is moving with an acceleration. Different frames of references can also move relative to one another. In fact, all motion is relative. Inertial reference frame. An inertial reference frame is where the laws of physics hold true. Newton's laws of motion can be used to describe the motion of objects, and there's no need for any fictitious forces. The observer must be moving at a constant velocity. So for example, it could be a rest, which is the rest frame that most people like to use. Maybe they're moving at 10 meters per second forward, or maybe they're moving at 20 kilometers per hour northeast. In the inertial reference frame, we have two observers down below here who are inertial. So we have the old flash right here at rest, not moving. So this is the rest frame of motion, which is an inertial frame of motion. And then we got the other flash moving at 50 kilometers per hour east, or to the right. And in this case, both these observers are going to describe the motion of this baseball. Okay, so the flash who's at rest would say this baseball is making a parabola, quadratic function. It's moving forward at 150 kilometers per hour. And it traveled up a certain height and then came back down. It's nice symmetrical quadratic function or parabola. And the only force acting on the ball is the force of gravity. So on the way up, it slows it down on the way up, and then it accelerates it down on the way down. And while that's going on, the ball's moving forward at 150 kilometers per hour and travels this distance right here. Observer 2, though, sees things a little bit differently. Because observer 2 is moving towards the ball at 50 kilometers per hour, and the ball was moving in the rest frame at 150, all combined, the observer 2 will see the ball approaching at 200 kilometers per hour. So it's going to be a little faster. So if you caught the ball, you would collide with your hand at 200, not 150, because you are moving at 50. So now it's going to have the same height as before, but now it's going to have the previous distance, plus it's going to look 33% longer, or 4/3. Why? Because 200 over 150 is 4/3, so it's going to appear to be moving faster. So it's going to cover a different amount of distance in the parabola. But still, there's only one force acting on it. It's the force of gravity. A non-inertial reference frame is a reference frame where the fictitious forces are needed to explain the motion. The observer must be accelerating. So for example, they start to fall down, so they're accelerating down at 9.8 meters per second squared. Or they hit the brakes on their car and they slow down at minus 11 meters per second squared. Or they push down on the accelerator or increase the thrust or the propeller, and they accelerate at 39.2 meters per second squared. So in the diagram below, we have two observers who are non-inertial observers. They're accelerating. So this Wonder Woman here, she's falling at 9.8 meters per second squared. And over here we have Iron Man accelerating up with his thrusters at 49 meters per second squared, or 5 Gs of acceleration. Okay, so observer 3, Wonder Woman. What's Wonder Woman going to see? Well, as the ball is falling down, Wonder Woman's falling with the ball. So according to Wonder Woman, there is no parabola. The ball is traveling in a straight line towards her. All right, so you can try that yourself too at home. You and a friend can jump off the couch while your friend throws you a ball, and you stare at the ball as you're falling to the ground. You see it stays the same position in front of your nose the entire time. So here we have two forces. We have the force of gravity pulling the ball down, but then we have some fictitious anti-gravity force, which is keeping it from falling so that it maintains a straight line. Okay. So now, this is the tricky one. How about Iron Man? Iron Man is accelerating up at 5 g's, or 49 meters per second squared, while the ball is accelerating down at 1 g. So altogether, there's a 6 g acceleration between the ball and Iron Man. So that's 58.8 meters per second squared. So as Iron Man's going up and staring at the ball going down, the ball's going down really quickly now. It's going to be going down at 6 g's relative to Iron Man. So we got the force of gravity providing 1 g. There must be some super ghost gravity or something, or some fictitious force pushing it down at another 5 g's. And so we get this extreme parabolic arch right here. Same length as everybody else, but now the height, whoosh, it's just going down there. Okay, so here's another example too. A linear example. So let's say you got a train which was moving slow at 1 meters per second, and there was a ball hanging from the train. And then the train accelerates forward at 4 meters per second squared. So you'll feel that pull backwards, and you'll have to brace your legs to keep from falling over. And the ball, which was attached to the ceiling, it's going to swing back. So if you're the non-inertial observer, you're going to say, oh, there's a fictitious force, some ghost force or something pushing the ball to the left. While if you're the inertial observer outside and you're looking through the window, you say, oh, the car just accelerated. The ball's inertia wanted to stay at a velocity of 1 meter per second. But hey, the string is pulling it forward. It's accelerating it at 4 with the rest of the train car. And then eventually the train decides to stop accelerating, and then the ball goes to hanging down normally again, while the train is now moving quickly. So the person in the train starts off as an inertial observer. During the acceleration, they're a non-inertial. And then when the train reaches its final speed, they become an inertial observer again. The person outside, though, is an inertial observer the entire time. So if the ball has a mass of 0.15 kilograms, or 150 grams, and the train accelerates at 4 meters per second squared, what is the angle of deflection? So what's this angle theta right here? And what is the tension on the string? So how many newtons of force pulling on the string at this point in time? Okay, so while the ball wanted to remain at 1 meters per second, but now it's accelerating at 4 meters per second forward. Okay, so in the y direction, we're going to break this up into x and y vectors. In the y direction, the force of gravity is pulling down, and the tension now has a y component up. So that's going to be the force of tension times the sine of the alpha angle there. So the tension up, subtract the force of gravity. The ball's not going to accelerate down or up. It's just going to sit there. So that's why the acceleration in the y direction is 0. So the tension up is going to be 1.47 newtons. Now in the x direction, we know it's accelerating the ball forward at 4 meters per second squared. And the only thing that's pulling the ball forward is the wire or the string. So the tension in the x direction will be the mass of the ball times that acceleration of 4.6 newtons. So now to find the actual tension in the string here, we have an x component and a y component. So we're going to use Pythagorean theorem. So the force and the tension squared is equal to the x component squared plus the y component squared. 0.6 squared plus 1.47 squared, add them up, square root, and we get 1.59 newtons. Now to find the angle. So now we have the x and y components. If we take the y component, which is the opposite, over the adjacent, the x component, we'll find the angle alpha, and we get 67.8 degrees. So if that's 67.8 degrees, then the angle between the ceiling and the string is 67.8, which means theta is 90, subtract 67.8, and that works out to 22.2 degrees. So the ball will be deflected 22.2 degrees. Now this type of device is actually called an accelerometer, where you hang a ball or a weight down a string, and when you accelerate forward, the angle of deflection can be used to determine your acceleration by just doing this question backwards. Okay. Alright, here's another example, a non-inertial rotational example, a merry-go-round problem. So if you're on a merry-go-round, you feel like you're going to be thrown off the merry-go-round by a fictitious centrifugal force. However, what's really happening is your body wants to keep moving forward, and your arms are pulling you inwards towards the center of the merry-go-round. So where would you land if you let go, though? Would you just fly yourself backwards and land back from where you came? Would you fly straight sideways and land on the ground? Or would you actually just continue moving forward and land in front of where you let go? And yes, that's the correct answer. So you have this fictitious force outwards, but you won't land outwards. You will land forwards. Alright, so here's a question. What if you have a 40-kilogram child? So this child is 40 kilograms. And the radius of this merry-go-round is 1 meter. And it takes 2 seconds to go around once. What is the force on the arms of this child? So your centripetal force is provided by the arm tension. So your arm's pulling yourself in. We got mass, and we got 4 pi squared r over t squared for the centripetal acceleration that uses period. So we got our 40-kilogram mass, 1 meter radius, and we have a, it's not a 2-second period, it's a 3-second period to go all the way around once. So in that case, it works out to 175 newtons, or 39.4 pounds. It's a lot of force for a kid. So yeah, definitely this had to be 3 seconds. You imagine 2 seconds, it would have been even more force. The poor child would have either dislocated their shoulder or gone flying off. So, 40-kilo child, if it is a 3-second period, will need 175 newtons, or 39.4 pounds of arm strength to stay on the merry-go-round. That is quite a lot of force for a child, and they'll have to hang on for dear life. So in summary, a frame of reference, or a reference frame, is where the motion is measured from. It is the coordinate system used by the observer, and most of us are used to the rest frame of reference, the ground, which is now moving. And we like to describe our motion from that reference frame. Now, an inertial reference frame requires the observer to be moving at a constant velocity, like 0 meters per second, or, for example, traveling down the highway at 100 kilometers per hour east. A non-inertial reference frame requires an observer to be accelerating, for example, falling, accelerating a vehicle, braking, moving in circles. Now, if you want to see some really good videos that explain that, there's this one from Ted on reference frames. So here's a link here, or there's an optional link there. And then the best video I've ever seen for reference frames was made in 1960 by the University of Toronto. It's black and white. It's right here. Awesome, awesome film. It'd be nice, of course, if they could redo this in color with modern equipment, but it does a great job of explaining reference frames. I just wish someone would redo it though, and make it a more modern version. And I hope this helps. Thank you.